So the second speaker is Dr. Tom Mo from University of Oxford, and he will give a presentation on the experiments in predicting early-stage Alzheimer's.
Is there a pointer? Yeah. Okay. Well, thank you for asking me to talk about my work. I'm describing some experiments that I've done in a project that is a collaboration between the Maths Institute in Oxford and the Department of Psychiatry. So what I'm going to talk about is predicting Alzheimer's disease and seeing how path signatures can help with this process. It's an application of machine learning. In fact, in the experiment I'm going to describe, I'm using a relatively simple statistical fitting approach. But in fact, what I'm talking about is features rather than the particular learning method. So the talk comes in 3 parts. I'm going to talk a bit about Alzheimer's disease and just set the context so that I can explain the experiment. I'm going to talk about the experiment itself and how I've used path signatures, and the kind of point of the talk is that what we get with path signatures is features that can be interpreted, and that's one of their strengths. So to talk a bit about Alzheimer's disease, the graph at the top is a typical progression through the symptoms of Alzheimer's disease. So it's taking place over the period of about a decade. The y-axis is this scale called the MMSE, which is the mini mental state examination. And a score of 30 on this is healthy. A score of 0 is unhealthy. So the disease starts off, Alzheimer's disease starts off with this condition called MCI, which is mild cognitive impairment. Not everyone with MCI goes on to develop dementia. In fact, a minority of people with MCI develop dementia. So the progression is through mild Alzheimer's disease through moderate to severe. So mild Alzheimer's disease is characterized by difficulties with cognition. Moderate is that there are some effects on behaviour and some impact on the individual's activities of daily living, the normal things that people do every day. Severe Alzheimer's disease is characterized by total dependence on another individual to feed themselves, look after themselves. So I should say that Alzheimer's disease it's a brain disorder. It's a kind of dementia. In fact, it's the most common form of dementia. And the disease process happens before this graph begins. So what is going on in the brain is happening years, if not decades, before the symptoms appear. So there's an interest in seeing if we can predict a diagnosis of Alzheimer's disease from, for example, brain imaging scans. So this is the cognitive scale I referred to earlier, where the score of 30 is a healthy score. So you can see that the kind of questions that are asked are: what year is it? Where are we now? Count backwards from 100 in 7s. So you can see that most people, if your cognition is normal, you're going to get something close to 30. Anything less than 26 is a sign of a problem. And in fact, in the experiments that I've done, I've found this scale to be quite a good predictor of a diagnosis. In fact, in this talk, I'm not using cognitive measures, I'm using brain imaging data. So this construct called mild cognitive impairment is important in these experiments. Mild cognitive impairment it's a clinical construct, and it's characterized by cognitive deficits, in particular memory loss. But one important aspect of it is that there's no evidence of dementia. And as I said, it's only a minority of people who have cognitive impairment who go on to develop dementia. In fact, some memory loss after the age of, 50 is normal. So I'm using brain imaging data as to derive features for prediction. And this shows what's going on in the brain with Alzheimer's disease. So that on the left we have a healthy brain, on the right there's an Alzheimer's disease brain post-mortem, and clearly the tissue on the right has shrunk. So there's this process called atrophy, which the disease causes. Atrophy means where the tissue degenerates. And from my perspective, the significant point is that the changes in volume. So there are a few regions of the brain highlighted here. The hippocampus is known to be important in Alzheimer's disease, and that shrinks during the disease process. There are these holes, these gaps in the brain. These are fluid-filled cavities that occur in every brain, and these get larger in Alzheimer's disease. So this is the data that I'm working with. There are 4 graphs here, each from an individual, and what they show is the brain volumes. They're from structural MRI data, which gives volume information for different parts of the brain. So this is from one individual here. The diamonds are diagnosis points. So these people are being monitored over a period of time. The x-axis here is months, and this is the brain volumes that are scaled to fit on the graph. So blue is the volume of the whole brain, red is the hippocampus, yellow is the ventricles. So 2 healthy people on top here, 2 people here with Alzheimer's disease. So the diagnosis occurs at this point here. So the red diamond is a diagnosis of Alzheimer's disease. Yellow is mild cognitive impairment. So the challenge is, how do we derive features from these graphs to make a diagnosis? So what I'm trying to do is predict this diagnosis point. So going on to just changing the application for a minute and looking at an example that's similar to the one that Terry gave this morning, just considering how one might get features from a path. Here I've got a letter B. So this has nothing to do with Alzheimer's disease. And I'm drawing the letter B from the top to the bottom. And the graphs below are the time series of the x and y coordinates sampled at regular points. So this is the original time series. In the middle is where we're drawing a bit faster at the start. And on the right hand side is where we draw a bit faster towards the end of the letter B. So so the point is that I could be using these time series directly and deriving features from the time series. But just like with the case with drawing the character, the actual time series are all different, and they depend on the speed of drawing. Now, if we're interested in the shape rather than the speed of drawing, then we want something that's independent of the time parameterization. And the signature provides this. So the signature in this particular case is this. So from a machine learning point of view, the signature provides a unique representation, in this case of a shape. So in the case of, so here's the definition that has been given earlier of the signature of a path, where you have these are the iterated integrals that Terry was talking about before. In the particular case of 4 dimensions, so I have 3 brain volumes and time, so I'm dealing with 4 dimensions. These are the signature terms, where the numbers are just the indices of the variable. So say number 1 could be the size of the whole brain, number 2 could be the size of the hippocampus, and so on. So what we get is a series of length 21, I think, which represent the individual variables, so the size of the brain structure, but also the interactions between those variables. So here we have 1, 1. Well, it's actually a square term, which is, but here we have one where we have the same variable. But 1, 2 could be, for example, the interaction between the whole brain and the hippocampus. So what's useful from my point of view is that this is an interpretable feature. So this is actually an interpretation of what some of these terms mean. So I'm talking, so where we have an interaction between two terms, I'm calling these cross terms. So let's say we have variable x1, variable x2. Again, that might be the whole brain versus the hippocampus. The cross terms show this is a geometrical representation of the cross term. So it shows how these variables are changing with respect to each other. And you can see that they measure a departure from a straight line. So they distinguish whether one variable is changing fast with respect to another. So to the experiment itself, what I'm trying to do is distinguish healthy individuals. So we've got one on the left here who's always got a healthy diagnosis, from someone who's getting a diagnosis of Alzheimer's disease. And here we have someone who remains with a diagnosis of mild cognitive impairment. So the challenge is to distinguish these sets of individuals. So what I'm doing 2 classifications. One classification of healthy versus Alzheimer's, a separate classification of Alzheimer's disease versus MCI. And I'm deriving the features from the path and also using the variables, the raw variables themselves. So I end up with a feature vector of 23, I think. The amount of data is relatively small, So I'm using lasso to select the features. So the point of this is to look at the features that are selected during training. So these are the training curves for on the left is Alzheimer's versus healthy, on the right is Alzheimer's versus MCI. And you can see the training, that the regularization parameter lambda is increasing to the left, and we can see there's some optimization. And we're looking at the features that are selected at this value of lambda. And these are the results. So there are two classification experiments. There's Alzheimer's versus healthy on the left and Alzheimer's versus MC on the right. Now in both cases the baseline value of the hippocampus is selected. We have these increment terms, which are the first order terms in the signature, but they so this is actually the increment in size in the time, and the increment in the size of the ventricles. And then we have these cross terms. So we have the change in the size of the ventricles over time is significant, and the change in the size of the hippocampus over time is found in both cases. And what's interesting is that we find that the change in the size of the hippocampus with respect to the whole brain is selected in both cases. So these are the features that are found are not surprising in the context of what's known about Alzheimer's disease. But what this illustrates is that you can, using the path signature, you can get features that can be interpreted. So just to conclude, you can use MRI time series to predict whether someone's going to get Alzheimer's disease. So in other experiments that I've done, the prediction accuracy is about 80%, and that's fairly typical for these experiments. This interaction between the whole brain volume and the hippocampus is quite interesting, because what it shows is that in people with Alzheimer's disease, the hippocampus is shrinking with respect to the whole brain abnormally quickly. And I think the main point that I'm making here is that with a lot of classifiers, you can get accurate results, but they may not necessarily be interpretable. If you encode the nonlinearity into the features, you can get accurate results which are interpretable. And that's all I've got to say. Thank you.
Is there any question?
Thanks, very interesting presentation. So when you say interpretability, what do you mean exactly? So is interpretability from a physiological point of view, or is interpretability as to you can tell the patient a decrease or a change in this feature will mean to you a deterioration of whatever?
Well, I think it's really from the point of view of physiology. So it's the relation between the variables that you can see. So, it's the. I think what it gives you is an ability to compare the different variables one with another in a way that other means of deriving features wouldn't. So this is two of second order terms in the signature. I'm not so sure about higher order terms. I don't know, does that answer your question?
Yes, thank you.
Is there any more questions? If not, let's go again.